Now, if we take a very simple approach, which is always the way to start, circulation patterns on a non-rotating Earth would look like this. So here we have high heat input at the equator. That heat is going to spread away from the equator and ultimately dissipate as it moves to the South Pole or as it moves to the North Pole. And vertically what's happening here is this. We have air moving from the high latitudes towards the low latitudes along the surface. It's heated, moisture is pumped in there, making the air low density. It rises and it spreads to the north, cools and sinks. So this is what we would see on a non-rotating hemisphere sitting in space with the sun located where you are. You're looking right at the Earth from your sunspot. However, this isn't the case because the Earth is rotating. And when we add rotation to this kind of simple scenario, we get this. We get a deflection of this circulation cell. This is known as the Coriolis Effect. It's the reason that this happens. So in the northern hemisphere, everything that's moving is deflected to the right. In the southern hemisphere, everything that's moving is deflected to the left. The rotation of the Earth on its axis is going to deflect the atmosphere towards the right and the north, towards the left and the south, resulting in these curved paths. The deflection of the atmosphere sets up a complex global wind pattern that drives the surface ocean currents. So it's not just the air that's moving as a result of the Coriolis effect. It's also the oceans that are moving from the Coriolis effect, and they're also driven by the influence of the Coriolis effect on the air, which makes it a little bit more complicated, as we'll see when we get to ocean circulation in a bit. Expanding on that last diagram, getting a little closer to reality here, we see atmospheric circulation and the Coriolis effect creating global wind patterns. These global wind patterns include the trade winds, which are located near the equator, blowing in this direction in the north, blowing in this direction in the south. They're called the trade winds because in the good old days, people would travel using these somewhat predictable wind patterns. So if you were to sail south from Europe, leaving, say, Portugal, sail south in the Atlantic, you would eventually catch the trade winds and you get a free ride to the west. Now you can't come back the same way because you're going against the trade winds, so you have to get to a higher latitude, and then you could ride what are called the Westerlies back towards Europe. So you sail south here, west here along the equator, move to higher latitude, sail back to the east on the Westerlies. So here we have atmospheric circulation and the Coriolis effect generating these global wind patterns. The trade winds, the Westerlies, they also force the jet streams, the 4 to 6 jet streams at any given time. Those are called geostrophic winds, and we'll take a bit of a closer look at that in a few minutes. Let's start out by looking at a non-rotating Earth. In this case, a rocket is going to travel along the Earth's surface. So we're traveling from the North Pole to a target, which would be the Galapagos Islands, it looks like. Now, if the Earth is not rotating, any vehicle you launch travel in that straight direction. However, because the Earth is rotating, the vehicle that you launch is going to tend to veer to the right. It's going to veer to the right because it's moving in the northern hemisphere, and the northern hemisphere is rotating, always curving to the right. If it was traveling from the equator to the pole, it would also curve to the right. No matter which direction you're traveling, curve to the right in the northern hemisphere, curve to the left in the southern hemisphere. I'm going to post a series of videos that should help you conceptualize this maybe a little bit better than I can with this particular diagram. Here we have a simplified diagram of what's going on vertically in the atmosphere. The general circulation of the atmosphere is such. We have convergence in some locations where air masses come together because there's a low pressure cell sitting there. When those air masses converge, they increase the pressure at that location. Divergence is air moving away from a region, spreading out. Here we have some Hadley cells located adjacent to the Earth's equator. Right at the Earth's equator, latitude of 0, we have convergence. Air is coming from the southern hemisphere, moving to the north, reaching the Intertropical Convergence zone, where it runs into, converges with, air coming from the north. When this air collides, and because it's warm and moist, it rises. This is going to create kind of a vacuum, holding your dust buster or your vacuum cleaner, your shop vac, over the surface here and pulling air upward. So there's a low pressure system right here at the surface. Air is rising. As this air rises, it becomes clouds, very tall clouds. As those clouds develop, eventually they cool off and precipitation falls. At that point, the clouds then move to the south, here in the southern hemisphere, and move to the north in the northern hemisphere, ultimately dissipating. They disappear. That begins during subsidence. So here air is moving downward. It's compressing upon itself. And because it's moving down and the pressure is increasing, it becomes less and less humid. Because it's less humid, you've removed those water molecules that have a lower weight compared to oxygen and nitrogen. The air becomes more dense. It's warm, which usually makes it less dense, but you've removed the water vapor, so now it's going to become more dense. It's going to override that temperature signal. So this air subsides because it's high density and low humidity. It's going to result in arid conditions at the surface here. A high pressure system would be sitting right here, as opposed to a low pressure system sitting here. Another high pressure system sitting here. So these are the 30 degree south, 30 degree north high pressure cells. They tend to remain throughout a year. They move a little bit to the north and south from 30, but they're pretty much tied into that latitude. So it's wet here because of all the precipitation associated with uplift. It's dry here because of subsidence. Now, if you're a scuba diver, you've experienced this when you fill your tanks. You take your tanks, you put them in a tank of water, and you add compressor hose, and you start filling those tanks, compressing air, smashing it down into that tank. In doing so, you're essentially doing this. You're compressing that air, and you're going to generate heat when you compress it. This heat is dissipated from the scuba tank into the water tank that you have the scuba tank stored in. This helps to keep it from exploding and other bad things that can happen. This is what happens, on the other hand, if you open up that scuba tank. As the air rushes out, it goes from high pressure to low pressure, and it feels cool or cold. You can do the same thing with your mouth on a smaller scale. You can actually produce a condensation cloud using your own mouth by compressing air in your mouth and then exhaling it at a lower pressure. It's kind of cool. We've touched a bit on the Intertropical Convergence Zone, the ITC-Z here in Canada, and the ITC-Z in the US and a lot of other places. This is where converging air meets in the tropics. Air, again, is streaming from the northern hemisphere towards the equator. Air in the southern hemisphere is streaming towards the equator from the south. They meet here at or near the equator, and upon that meeting, there's uplift. When this air is uplifted, it cools, forms clouds, and ultimately precipitation that falls pretty much every day. This Hadley circulation that's come to be known has air converging in the tropics at the surface, rising. As it dries out, it diverges and descends at 30 degrees north and 30 degrees south. And this is going to be pretty predictable, except in Southeast Asia. The reason it doesn't work so well in Southeast Asia is we have the Tibetan Plateau, which sticks up about 20,000 feet. That would be 6,000 meters or so 6 kilometers into the atmosphere. This big block that sits 6 kilometers up, being about the size of the United States, it's a very large disturber of the atmosphere, or interrupter of the atmosphere. It doesn't work quite so well in Southeast Asia. And we'll come back to that a little bit later. It's actually depicted in Forrest Gump, if you've seen that movie. They don't quite put it this way, but That's what's happening. This brings us back to the topic of latent heat. We've been poking at this subject for a couple of segments of lectures anyway. What this is latent heat resulting from heating of tropical water is the mechanism driving convection. This is most regularly seen and most readily seen in the large convective cells that are generated in the tropics in the afternoon. And one of the cool things about going to the tropics is seeing these huge clouds develop starting in the early afternoon, becoming really, really impressively gigantic and ominous as it's about to get dark. The lightning becomes obvious, hundreds or thousands of lightning strikes, very, very heavy rainfall, sometimes hail, usually it's rainfall in the tropics, falls from these high, well-developed clouds. And this is how it works. So we start out with the Cumulus Cloud, in this case, a towering cumulus cloud, which ranges in altitude from a few thousand feet, a few hundred meters above the Earth's surface, expanding upward. As it expands upward, lower and lower pressure is generated here near the surface. That causes more air to stream in from the right and from the left. As this wet, warm air streams in, it produces an even more buoyant air mass that rises further and further. Eventually, we can get a tower that breaches the top of the troposphere and extends into the tropopause, almost into the stratosphere. At that point, these clouds become flat on the top. They develop that characteristic anvil shape, the Cumulonimbus Cloud. So here we see a height of over 40,000 feet. This is higher than any airplane most of us travel on will go into the atmosphere. They steer around these kinds of events rather than fly over them. These very high towers generate very strong winds. This uplift generates very low pressures at the surface, therefore lots of air streams in. That air is wet, it's warm, it goes rocketing upward to incredible heights where it's much, much colder than at the surface. By cooling this air mass off, making it really cold, most of the moisture in that air mass is converted into precipitation. It can start falling as rain, but if it's falling here in an area of uplift, that rain may be pushed back up. If it's pushed up repeatedly, it could become hail. If it's a very, very strong updraft, hailstones can become as large as tennis balls, softballs, even bigger than that. Is a very, very strong vertical wind, over 120 miles an hour, blowing straight up. Eventually, these clouds are going to lose their moisture, and at the same time they lose their latent heat. That heat is going to be given off during this precipitation event. Because this precipitation event happens rapidly and there's a lot of air involved, there's a lot of latent heat, and that helps fuel this uprise, this lifting of the air mass, because of all that heat is pumped out at a high altitude. So this is a self-sustaining system for a while. At the mid-latitudes and high latitudes, circulation is a little bit different. The air masses at the pole are cold and dry, and this is even more so the case in winter times. And the net result is we have high pressure, clear skies, subsidence, and movement of the air masses towards the equator. So these very cold, very dry air masses that form at the very high latitudes head south towards the equator. And they're going to generate the crazy storms we get here in the mid-latitudes. So in this case, we have a polar front zone with a steep temperature gradient at about 60 degrees north. So this would be right around the northern border of Saskatchewan, where this is focused, and about 60 degrees south. This is where the cold polar air meets warmer subtropical air. The cold dense air, because it's cold, because it's dry, it's very dense, it's going to force its way like a bulldozer or a snowplow underneath the polar front zone. The cold, dry, dense air is going to ride underneath the rising warm air, force that warm air up, and we're going to get mid-latitude cyclones, high-latitude cyclones. These are storm events, storm cells that could generate fairly simple precipitation events all the way up to derechos that we saw wreck Iowa and the rest of the Midwestern U.S. a few weeks ago could generate tornadoes. Further in the south, over a source of warm water, we could start hurricanes. Weather occurs where air masses of different densities and different chemistries come together. There's some kind of conflict. Now, building on those other diagrams, we're now going to add the polar front. So we have the Hadley cells here, we have Ferrel cells here, and the polar front zone located here. So again, rising air here, low pressure at the surface, diverging here, subsiding here, hitting the Earth's surface or getting close to the Earth's surface, and then spreading out again, diverging. Some of this diverging air moving to the south is going to run into cold polar air from the high altitudes of the center of Antarctica. That air is going to slide underneath this mid-latitudinal air and generate storm fronts, precipitation action here. Same things happen here in Europe and North America, as well as Asia in the northern hemisphere, where we have high pressure diverging at near the Earth's surface, moving to the north, where it's going to run into cold, dense polar air masses, sliding underneath, lifting this warm air, generates precipitation, generates wind, because we're generating a low pressure cell near the Earth's surface. So storms occur where the pressure is low, sunny skies where the pressure is high. So just another way to look at this here is we have the equator with the intertropical convergence zone. So uplift here, this air dries out and spreads out, moves to the north, starts to subside. Where this starts, we have the subtropical jet stream. There's not one jet stream, there's not two jet streams, there's usually 4, sometimes 6 at any given time. The subtropical jet is going to drive climate conditions at around 30 degrees north and 30 degrees south. The polar front jet is what we deal with here in Saskatchewan. This polar front jet is going to cause weather situations from around 60, 70 degrees north down to around 40 degrees north and even a little further to the south. But as we'll see, this polar front jet, also known as the Circumpolar Vortex or the Polar Vortex or the Vortex, these are all names that have been around for a long time, but suddenly they've become cool to throw out there. These are going to generate the jet streams that we travel in. The reason they're called jet streams, they were discovered in World War II. Sometimes pilots would get to a bombing location too soon, and sometimes they would run out of fuel leaving a bombing location because it was harder to get back. And it turns out, ultimately, they determined there were masses or tubes of high-speed air traveling through the atmosphere. If you pop your plane into one of these that's moving east and you're traveling east, you can pick up a couple 100 miles an hour or a couple 100 kilometers an hour for free just by putting your plane in this tube and going for a ride. Now, if you're coming the other direction, you want to avoid that tube, because that means if your plane is flying at 500 kilometers an hour and you're running in the center of a polar front jet that is 250 miles an hour, you're spending fuel to go 500 kilometers an hour. You're spending fuel to go 500 kilometers an hour, but the wind's blowing against you at 250. So the net result is you're spending 500 kilometer an hour of fuel on going 250 kilometers an hour. Hope that makes sense. As we come a little further to the north, this is where the mid-latitudinal warm, moist air masses run into these polar cells with very cold, again, very dry air, pushing their way underneath the warmer subtropical air, lifting that air, causing yet more storm cell development. So storm cells here regularly at the equator, storm cells here associated with this polar jet away from the equator. And because this wiggles around north and south quite substantially, this can happen over a wide range of latitudes, pretty much from way up here down to around here, sometimes even lower. When it happens below 30 north, that's when you get crazy freezes in Florida, where you see orange groves with frost or icicles on them, and fish die off because they're tropical fish. Now here's one of the coolest diagrams, one of the coolest animations we'll see. Let's take a look at wind. When we add Hadley cell circulation, what you'll see is the air converging near the equator and then rising. This air is rising because it contains significant moisture. It's also rising because the equator receives more insolation per square meter than any other place on the Earth. So by coupling this moisture with this low density caused by the high temperature, we get an uplift. This uplift picture here is the Intertropical Convergence zone. So significant cloud formation, we have divergence. After the precipitation drops, the air then descends. As it descends, it compresses. As it compresses, it becomes warmer. As it becomes warmer, it becomes less and less humid. So it starts out with relative low humidity. As it descends and gets warmer and denser, it becomes even less humid. When we throw in the tropical and mid-latitudinal components, you'll see some additional complexity here. Coupled with the Hadley cells, we have the development of the northeast trade winds in the northern hemisphere and the southeast trade winds in the southern hemisphere. These again are deflected to the right, no matter which direction they're traveling, because of the Coriolis effect. That's in the northern hemisphere. In the southern hemisphere, they're deflected to the left. Now, what this results in, this increase in pressure as the air is descending, is a standing high pressure system at about 30 degrees north. You notice that off the west coast of North America here, this provides the Southwest with a relatively dry climate. Over here in the Caribbean and the Atlantic, you'll see another standing high pressure cell. This forms the dry, low wind environment over the mid-latitudinal Atlantic. As we move higher in latitude, we'll see a development of the Westerlies. These are the winds we're familiar with here in Saskatoon, or anywhere along the northern tier of the United States or southern tier of Canada. The winds generally blow from the west to the east. So winds that are traveling to the east are called westerlies. Winds that travel to the west are called easterlies. Not my idea. Meteorologists did that to you. Now we're going to throw in the high latitude components. We see the polar front appear. This ring of cool air is going to be associated with a collision here with warm air coming from the south. So cold air coming down from the North Pole is going to run into warm air moving upward from the mid-latitudes. And where these air masses collide, the cold air, being denser, is going to slide underneath the warm, wetter air. This is going to result in uplift that you see here. This uplift is going to be a persistent band of precipitation, whether it's rain in the summer or snow in the winter. It's going to be precipitation tending to fall along that band of colliding air masses. Now, one last complication here, we throw in upper atmospheric flow. You'll see 4 bands or 4 tubes of this high-speed air located here in the northern hemisphere, subtropical jet stream, polar front jet stream located here. This polar front jet stream is going to be what we're familiar with on nightly weather forecasts. This high-speed band or tube of air is going to flow from the west to the east, and being the jet stream, this could be an air tube that an airplane gets into if traveling to the east, high-speed air tube that the airplanes would avoid if they're traveling to the west. And again, we'll see that a subtropical jet here in the northern hemisphere, another subtropical jet down here in the southern hemisphere, and another polar jet here in the higher southern latitudes. So that's kind of cool.